Hello. Today I'm going to show you how to do addition in floating point, specifically in single precision. The process is the same in double precision. It's just that you'd use 1023 here, 1023 to normalize and denormalize the exponent instead of 127, which is for single precision. So first I'll explain the steps, and then I'll show you how to solve this here. First step is you want to copy the sign bit from the number with the bigger exponent value. So basically, you have to take a look at these two exponent values and then see which one is bigger. Just looking from this is the bigger exponent value. So you'd want to copy 0 here. If this was 1, you would copy 1. And if this was 1 here, then you wouldn't copy that because this is smaller. This is smaller because this is just 128 plus 2 plus 1, which is 131. But this is 132, which is 128 plus 4. So this is the bigger value. If both of them were negative, it would still be the same. This would be 1 because this is the bigger value. Next, we want to determine the value of the exponent and denormalize it. So again, since this is 132, to denormalize it, you'd have to do 132 minus 127. And then that's going to be 5, right? And then this here, that's going to be 131 minus 127, which is going to be 4. So just keep those in mind. And then you want to convert the mantissa part to 1.m. Then we have to use the bigger exponent as a reference to add and subtract. Then we get the new mantissa and copy it and move it to the exponent part. So I'll show you that in a minute. Right now, I'll show you the process here. So first thing, we copy the sign bit from the number with the bigger exponent value. So just looking at these is obvious. If you don't know why, go check out the binary number systems video. So just write 0 here. After that, we determine the value of the exponent and then denormalize. This is 132, this is 131. So just subtract that by 127, and then we do the same with 131. This is going to be 5, and this is going to be 4. And then we'll set these to the side here. After that, we want to get the mantissa part and then have it in 1.m format. So 1.0001101, then 1.0100100. After that, as you can see here, you see these values. This is what we're going to use to append these and then do addition. So what did I mean by this? So remember when we convert to IEEE floating point, this is multiplied by 2 raised to the exponent. In this case, this is going to be 2 raised to 5, and this is going to be 2 raised to 4, because this is where we got them from. So I'll just move this here. After that, we can start adding them. So step 4, use the bigger exponent as a reference and add and subtract. So you know from the laws of exponents, we can't add this just yet because this is a smaller exponent than that. So what we're going to do is we're going to use this here, and then we're going to add that by 1 and then shift it to the left. So it lines up here. So let's do that. I'll just move that back to the right, and I'll use a different color. So now that's going to be 1.0001101 times 2 raised to the 5, and instead of 1.01, that's going to be 0.10100. Well, since this is 0, we can just ignore that. That doesn't really matter. Times 2 raised to the 5 now. See, that's why in this part here, it says copy the bigger exponent part, because we're not actually altering the exponent here. We're just matching it with the bigger one. So now let's do some addition. So starting from right to left, that's going to be 1 1 1 1 1 0 1.1. This is going to be our new mantissa here. So I'll just move this to the side. Then I'll use a different color. So the new mantissa is going to be this part. So let's write that down. 1 0 1 1 1 1 1. Yeah. All right. Now after that, we just copy over the bigger exponent. Actually, I can just copy that over. And remember, this is supposed to be 23 bits, right? I'm not going to show you that, but so that's how you add. Subtraction is just the same, except, well, you have to shift to the right instead, because these are going to be negative, right? Quick note here, just to show you what would happen if this was negative, like I mentioned earlier, is that you'd have to keep shifting to the left until it matches the exponent. So a good way is finding the absolute difference between the two. The easier way of getting the absolute difference is just by adding them. Get the absolute value of 2, and then add that by the absolute value of -1. So that's going to be 3. So we want to shift to the left 3 times. So shift once, there's a 0 there. Shift twice, there's a 0 there. And then shift 3 times, there's another 0 there. So this would become 0.00111000110. And then we just copy the one from earlier. And then just add by zeros. 2 raised to 2, and this becomes 2 raised to 2 now. And if you wanted to make this -1, you just have to shift to the right. So that's 2 raised to 1, 2 raised to 0, 2 raised to -1. As you can see, same as here. So that's a neat little trick you can use. After that, you just add normally. So 0 to 0, 0 and 1, 0 and 1 again, 1 and 0, 0, 1 and 0, 1 and 1 makes it 2. 3 ones, that's going to be 1 1. And then 0, then a 1. It's going to be the answer. And now, if you'd like, you can actually check if this is true or not. So let's just get the mantissa part here. That's going to be 1.1011111. And then this is going to be 5, right? Because that's 132 minus 5. I mean, minus 127. That's going to yield us 5. So 2 raised to the 5. Now, this number is what's going to dictate how many times we're going to shift to the right to get our normal number back. So 1, 2, 3, 4, 5. So 1, 1, 0, 1, 1, 1, then 1, 1. So given these real numbers here, that's going to be 55.75. So let's try and convert that here. So this is going to be 1, 2, 4, 8, 16, 32. 32 plus 16 plus 4 plus 2. That's going to be 55. And then the 0.11 part, that's going to be 2 raised to -1. So that's 0.5. And then 0.25. 0.5 plus 0.25, that's going to be equal to 0.75. And if you take a look, 55 plus 0.75 is 55.75. So that's the same answer as this, and as this. So you know that's correct.